Imagine looking up and seeing a star that should be impossible. A star that shines with the brilliance of our own sun, yet its core is cold. Not nuclear fusion, not hydrogen or helium. It shouldn't exist, but the math says it does. The terrifying truth is that some of the oldest, largest objects in the universe are not powered by light and heat as we know it, but by annihilation. Pure, invisible dark matter is fueling the most powerful engine in the cosmos. In the next 8 minutes, we are going to dive into the existence of the dark matter star, a theory that challenges everything you were taught about physics and cosmic history. This is how the impossible became plausible. For decades, physicists have wrestled with the ultimate cosmic debt. 85% of the universe's mass is missing. We call it dark matter. It doesn't emit, reflect, or absorb light. It's the invisible foundation of reality. We know it's there because of its immense gravitational influence. It pulls galaxies together, shaping the very structure of the cosmos. Without it, everything would fly apart. We know what it does, but we don't know what it is. The leading candidate for this phantom mass is a family of hypothetical particles called WIMPs, weakly interacting massive particles. Billions of these particles are passing through your body right now, completely undetected. Now, picture the earliest days of the universe, moments after the Big Bang. Gravity began to pull this dark matter together into massive halos, acting as the colossal blueprints for the first stars and galaxies. But here is where the impossible star enters the picture. What happens when the first massive hydrogen clouds form inside one of those dense dark matter halos? The answer is unlike anything you learned in school. What forms is not the sun we know, but something far stranger, fueled by the very particles that define its structure. A regular star, like our sun, ignites when immense pressure causes hydrogen nuclei to smash together in a process called nuclear fusion. It's a slow, controlled hydrogen bomb. A dark matter star, or D star, skips that crucial step. Instead, as the nascent star gathers gas, the crushing gravitational force of the core traps the surrounding dark matter particles, the WIMPs, in extraordinary density. The result is cataclysmic. When two WIMPs collide, they instantly annihilate each other. This annihilation releases intense amounts of energy, generating light and heat. This process creates a star that is incredibly stable. The energy released by the annihilating dark matter prevents the core from heating up enough to initiate fusion. It becomes a permanent, non-nuclear reactor. The truly mind-shattering fact, these stars could theoretically burn for billions of years without consuming their own fuel. They only require the constant influx of dark matter being pulled in by their own gravity. Their surface temperatures and luminosity could be virtually identical to a regular star, making them incredibly difficult to distinguish from the Earth. In essence, we may have been looking directly at these impossible stars for decades, mistaking them for fusion-powered celestial objects. So if they look exactly like normal stars, how could we possibly find one? This is where the hunt moves from astrophysics to particle physics. Scientists theorize that the only discernible difference is their internal structure. Because they lack fusion, they remain exceptionally massive and cool in their centers, and they never progress through the standard stellar life cycle. The most likely place to find them is among the first generation of stars, known as population 3 stars, which formed when the universe was just a few 100 million years old. These early stars were gigantic, hundreds of times the mass of the Sun, and contained virtually no elements heavier than hydrogen and helium. If any of them contained a dark matter core, they would still be shining today. The key signature is not light, but gamma rays. When WIMPs annihilate, they leave behind high-energy gamma ray bursts. Telescopes like the Fermi Gamma Ray Space Telescope are meticulously searching the ancient sky for this fingerprint.
The observation would not just confirm a new type of star, but would finally validate the existence and nature of dark matter particles. It is a high-stakes search. Find a dark matter star and rewrite 85% of cosmology overnight. This brings us to the ultimate question. What do these impossible engines do to the history of the universe? And is our Sun next? The theoretical existence of D stars changes the timeline of the early cosmos. They would have formed faster and lasted longer than conventional stars, radically altering the chemical composition of the first galaxies. Furthermore, these massive, stable dark matter stars could be the true progenitors of the first supermassive black holes. When a D star finally runs out of dark matter fuel, a process that takes billions of years, it would collapse. The gravitational collapse of such a massive object, free from the turbulent fusion process, is the perfect scenario for forming the seeds of the monstrous black holes we observe today at the center of every galaxy. This single discovery, the existence of a star powered by self-annihilation, would be a new cosmic rulebook, turning fiction into fact. If they exist, they are everywhere, lurking in globular clusters, hiding in the Milky Way's halo, or shining deceptively across billions of light years. The search is relentless because the reward is the fundamental understanding of reality itself. We are at a turning point in astronomy where the invisible mass that holds the universe together may also be fueling its most mysterious light sources. So, whether it's a tiny WIMP particle colliding in the core of a star or the collapse of a titanic cosmic structure, the mystery of dark matter is tied to the most extreme environments in space. If you found this mind-shattering, then you need to see the latest video on our Deep Space playlist, where we break down the biggest black hole discovery of the year. Click the end screen now to keep exploring the unseen universe.